All right, just recording a little video here, hoping to be able to help with a few questions. International rules of table tennis specify that the ball must bounce up to 24 to 26 centimetres when dropped from a certain height onto a steel surface. Balls are designed and manufactured to have a mean bounce of 25. So let's choose a pen that's not going to be quite so distracting. As much as I love the rainbow pen and all the other pens, let's maybe this one. Well, that's not bright enough either on the background. One more go. Pink should show up well. There we go. Mu equals 25. And we need to know between 24 and 26. That's what we need for a ball to be deemed acceptable. Feedback from competition organisers indicate that 4% are rejected because of their unsatisfactory bounce. Given that bounciness is normally distributed, find the standard deviation of the distribution and state any assumptions you make. Well, okay, I guess they're designed to have a mean bounce of 25, so I'm going to assume that's true. And I'm going to assume as many are rejected for being too bouncy as not bouncy enough. Now, whether I have to assume that or whether I can deduce that because they've suggested that they're normally distributed, which they've told us, and that the mean is 25, I think it's reasonable either way. Okay, so we've got this little area here is 0.02, and the other little area outside the range is 0.02. Given that we have 4% being rejected, that's 2% at either end. That's an equivalent distribution to a standard normal distribution. Mu equals 0, sigma equals 1. That's right, our distribution of z-scores. And what we want to do is we want to find the z-score that correlates to 24. So it's got 2% on the smaller than it. And we want to know the z-score. Oh, I was hoping to get rid of all of them. That didn't work. Surely I can close that little bit as well. There we go. And we want 2%. We want to find the z-score that corresponds to a 26 centimetre bounce. And that way we'll be able to go ahead and find our answers. So you go to your calculator and you do inverse norm. Oh, sorry, we can do... Yep, inverse norm. And what we're going to be looking for is our tail. Now you could do it for any of them. You could say the tail is 0.0, the area is 0.02 and the tail is to the left. The area is 0.02, the tail is to the right. I'm just going to do the tail is central and the area is 0.96. And when we do that, it spits out a couple of z-scores for us. A lower one and an upper one. Now, I think, I don't have my calculator in here with me, but I'm pretty sure it was negative 2.053 for the z-score corresponding to 24, and obviously positive 2.053 for the z-score corresponding to 26. So from here, you can set up simultaneous equations using your z-score, which equals the actual score minus the mean divided by the standard deviation, and you can fill in the information and go ahead and solve it that way. And it works beautifully, it works fine doing that. I could do that with either of the two z-scores. I've got an actual score. So for instance, I could go negative, oh, my stylus just decided not to come up, there we go. Negative 2.053, that score corresponded to an actual score of 24 when the mean is 25 and the standard deviation was sigma. And we can get sigma that way, going ahead and solving that. Alternatively, you can just say, well, the number of standard deviations between these is 4.106. If I just add those two together. And so that 4.106 lots of the standard deviation is equal to the gap between the two measurements, which was 2 centimetres. Whichever way you like to think about it, you should come up with sigma equaling 0.487. Which is all they were asking us for, I believe. They just wanted us to know the standard deviation. Find the standard deviation. Of course, I would go ahead and check that. I think if you check and you look up normal CDF, normal cumulative distribution function. So I think maybe on the Casio it's just NCD, but you got the idea. And we have a lower limit of 24, an upper limit of 26 on the Casio. For some reason they put the standard deviation first, 0.487, and your mean of 25. And I think when I checked that, it came out to be 0.96. So that's what we wanted. So that's the first one there. Let's have a look. We've got a couple more questions to go. We'll see how we go on those. Once it lets me in. Here we go. So this is QTE Test C, Paper 2, Question 18. Research assistant found the 95% confidence interval for the proportion of rats who could find their way through a maze under a minute. So the 95, this is our confidence interval formula from, give me my pen and let me, there we go, confidence interval from our formula booklet. You take the mean, in this case that's your sample mean, with proportion, and then it's the z-score. So what we need for this is, of course, the z-scores for a 95% interval and a z-score for the 90% interval, because the z-scores are different for those. And again, you can do that using inverse normal tail central. We do it the same way. The 95% interval, I believe the z-score for that I wrote down somewhere. I think that's the one you probably are fairly comfortable remembering as well. Did I write it down here? I have to go and find it. Oh, I've got it there. There it is. 1.96. Standard deviations, both above and below the mean. And then for a 90% confidence interval, it's 1.645. So we've got our two z-scores there. The p-hat we've been given, or we haven't been given, but we can work out. Confidence intervals are symmetrical. So p-hat is going to be halfway between 0.1907 and 0.4493. Add them together and divide by 2, and we obtain p-hat equaling to 0.32. So 2 p-hat equals 0.64 when I add them together, and then, yep, p-hat is 0.32. I can go ahead and find 1 minus p-hat is 0.68. It's still not going to help me because I don't know how many people are in here, so I'm not ever going to be able to find that n, but it's not going to affect my ability to get to an answer. And let's have a look why. Because I know that our p-hat, 0.32, plus 1.96 times the particular value p-hat 1 minus p-hat over n, that's this calculation I've got right there, that's equal to the right-hand side of the confidence interval they gave us, 0.4493. So we can go ahead and figure out exactly what this value is. The p-hat 1 minus p-hat divided by n, that's going to be 0.4493. First I have to subtract the 0.32, then I had to divide by 1.96. And so this particular value, p-hat 1 minus p-hat divided by n, is approximately equal to 0.065969. I wrote this on a little mini whiteboard before I recorded it for you, and I hope that I can read it correctly because it's all been mostly rubbed off But that's okay, that lets me find that. So then my actual 90% confidence interval, I'm just going to use that information. So my p hat, well, the mean is still the same. So it's going to be 0.32 plus the Z score is going to be 1.645. I needed to do minus for the first one. I was getting excited and doing the upper bound. Need to do the lower bound first. Minus 1.65 times this particular value, which we just found out, 0.065969. And then, of course, the upper limit, 0.32 plus 1.645, 0.065969. And if we simplify that, I make it 0.2115 and 0.4285. And that's our 90% confidence interval. Hopefully that made sense and you can follow along with that one. One more question to go for this little session. Let's hope, question 19, that looks like the one I'm after. Graph below shows part of a curve, y equals 2x squared. The tangent at the point where x equals 1 cuts the axis at t, determine the shaded area. Okay, well, it would be nice if I knew the actual coordinates there. I know the x coordinate is 1. To find the y coordinate, substitute it into the equation, because not only is it on the tangent, it's also on that line. And when I let x equals 1, I can find the y coordinate of that point is 2. This particular point has an x coordinate and then a y coordinate of 0. That's going to be useful for us. I've got a tangent line. I want to be able to find where it cuts the x-axis. I'm probably going to need to know something about that line other than the point where it contacts the curve. And of course, the other thing we need to know is the gradient. Well, the gradient of the tangent is equal to the gradient of the curve at that particular point. When I do the derivative, I get dy dx equals 4x. Therefore, when x equals 1, dy dx equals 4. So therefore, the gradient of the tangent is 4. If I'm considering my point t here, and I know that it has the x coordinate of t and a y coordinate of 0, and I've got another point on the tangent 1 and 2, I can therefore use my gradient rule. Difference in the y coordinates, 2 minus 0, over difference in the x coordinates, 1 minus the x coordinate at point t. That has to equal 4. Well, it's not going to be very hard for you to figure out that, well, I could go through the motions, I guess. 2 equals 4 minus 4xt, subtract the 4, negative 2 equals negative 4 times xt, divide by negative 4, and a half equals xt. You could just use rise over run and say it's gone down 2. How far backwards would it go? Well, if the gradient's 4, 2 divided by a half gives you 4, and you could have got a half straight using, just using your head. That would have been fine too. They've asked us to find the area. Well, now that I know that particular point is actually 1/2, 0, I'm going to be able to go ahead and find the area of the triangle. Area, of course, is 1/2 times the base, which is 1/2 a unit wide, times the height, which is a height of 2. And so the area of that triangle is exactly 1/2 of a square unit, whatever the units happen to be. So to find the shaded area, that's going to be the integral from 0 up to 1 of 2x squared dx minus the area of the triangle, which we just calculated as being 1/2. Now, if I do the integral of this, I'm going to have 2x cubed over 3, substituting in the 1 and 0 in a second, and then I'm going to subtract a half. Well, when I substitute in 1, I just get 2/3. Substituting in 0, I get 0. I still have to subtract a half at the end. 2/3 minus 1/2 is 1/6, so it's 1/6 of a square unit. And that's our shaded area. Hopefully you found that helpful. Keep up the hard work. Well done everyone on all your good efforts, and we'll see you next time someone needs help. Cheers.